Hello learners, welcome to this course on Embedded System Design using AT89C51 Microcontroller. In this tutorial, I will be discussing about on how to interface a temperature sensor with the microcontroller. So the temperature sensor which we are going to use is LM35. So a LM35 is a temperature sensor which measures the temperature value and gives a corresponding voltage as an output. So here I show a pin of LM35 which has 3 leads. So pin 1 is a supply to the temperature sensor which can support from 4 volt to 20 volt. And the pin number 2 is the output voltage which we get in respect to your temperature. Pin number 3 is a ground line. So we will be connecting pin number 1 to a supply, pin number 3 to ground, and pin number 2 will be connected to your ADC. ADC 0808 IC 8-bit A to D converter we are going to use in this experiment. So A to D is an analog to digital converter which converts your analog value to a digital value. So here it is a 8-bit ADC, so you will get a 8-bit output. So we are going to interface LM35 to IN0 pin of your ADC 0808 IC. So here this ADC, it supports 8 channel. Out of 8 channel, we are going to connect the sensor to the channel 0, which is IN0. So once my data is connected, once the sensor is connected, then after we start the conversion process, a 8-bit digital output will be coming from your ADC, which is coming from your out1 to out8 pins. Out1 represents the MSB bit and out8 represents the LSB bit. So this 8-bit value can be read through your port 1 of AT89C51 microcontroller. So after reading this value, we can convert this digital value into an analog voltage, and that analog voltage can be converted into a temperature and it can be sent to an LCD. So for this experiment, we are going to use Micro C Pro for AT51 as an integrated development environment, where we will be writing our embedded C program, convert that embedded C program into a hexadecimal file, and we will be building our circuit using Proteus 8 professional simulator. So once a circuit is created, we can import that hexadecimal file which we have created using Micro C Pro for AT51 into this Proteus 8 environment, and we can check the result. So if we see the features of your LM35, so it provides 10 millivolt variation per degree centigrade. So for example, if the room temperature is 30 degrees, then it will produce a voltage of about 300 millivolt. If the room temperature is 27 degrees, it will produce a voltage of about 270 millivolts. So this temperature sensor can be used for measuring a temperature range from minus 55 degrees centigrade to 150 degrees centigrade. And it provides an accuracy of about 0.5 degree centigrade at 25 degree centigrade. And we know that it operates with a voltage range from 4 volt to 20 volt. So for this experimentation, we are going to connect at the supply voltage of 5 volt. So after the conversion process, a 8-bit digital data will be obtained. So that digital data needs to be converted into a voltage value. So in order to do that, what we do is we take the digital value, ADC value, and multiply it with the ADC resolution. So the resolution is the smallest voltage change which can be represented in a proper binary bit pattern. So this resolution can be computed using this formula. So resolution is equal to V reference divided by 2 power n minus 1, where this n stands for what type of ADC it is, whether it is a 8-bit ADC or 10-bit ADC, 12-bit ADC. N represents the number of bit output coming from your ADC. Since we are using a 8-bit ADC, so we will have the resolution computed using 5000 millivolt divided by 2 power 8 minus 1, which comes about to be 19.61 millivolt. So this is the smallest voltage change which can be measured by our ADC without any errors. So if the voltage is less than this, then we need to do an approximation. Either I have to go to a lower representation or a higher representation of binary value. So for example, let us take our ADC value is 00001111, which is in decimal 15. So what is the measured voltage? 15, which is the ADC value, is multiplied by the resolution of your ADC, which is 19.61 millivolt. So it comes about to be 294.15 millivolt. So we need to convert this voltage into temperature. We know that for every degree centigrade, our sensor will produce 10 millivolt variation. So we need to divide this voltage by 10 to get the temperature. So if I divide 294.15 millivolt by 10, you will get 29.4 degree centigrade as a temperature value. So this is a typical circuit which we will build in Proteus 8 Professional. So where we use a AT89C51 microcontroller, and we are going to connect an oscillator frequency of about 10 megahertz connected to XTAL1 and XTAL2. And we have also connected a reset circuit to the reset pin. So by default, this reset pin will be at logic low. Whenever I press the switch, the reset pin will go to logic 1, thereby reset operation will take place. So on the left bottom, I am going to show the ADC circuit. So this is a ADC 0808 8-bit A to D converter. So as I said, here you can see it has 8 channels, IN0 to IN7, and we are going to connect LM35 to IN0. So where the pin number 2 of LM35 is connected to IN0, pin number 1 is connected to supply, pin number 3 of LM35 is connected to ground. So in order to select this channel, we have to provide the address. So the address can be given through A, B, C. So if I specify a value of 000, IN0 will be selected. If I give 001, IN1 will be selected. If I give 111, IN7 will be selected. So depending upon the value in this address A, B and C, a corresponding channel will be selected for conversion. So in order to latch this address, we use ALE signal. So ALE is address latch enabled. So if I give a value of 1 to this ALE, this address will be latched. Whatever value is retained on this address A, B and C will be latched by this ADC IC. Then we are going to use the reference voltage of 5 volt. So reference plus is connected to 5 volt and reference minus is connected to ground. And this conversion of ADC happens with respect to the clock signal. So this ADC 0808 IC can support up to 1.2 megahertz clock frequency. So for this experimentation, I am going to use 500 kilohertz as a clock frequency. Then we have a start the conversion process which needs to be provided from our microcontroller. So the microcontroller will say start the conversion process. So once the conversion starts, after certain time duration, the process will get completed. That will be indicated by the end of conversion process, EOC, end of conversion process. So this end of conversion process should be read by our microcontroller, because our microcontroller should know at what time to read the result from the ADC. That will be indicated by the EOC signal. Then we have out1 to out8. As I said, this out1 to out8 is nothing but the 8-bit digital value of your sensor data. So this out1 is a MSB, out8 is your LSB. So it is connected to your port 1 of your microcontroller. And there is an output enable pin which needs to be connected to a supply so that the output comes through this out1 to out8 pins. So here we are going to connect an LCD, 16 cross 2 LCD. So in the 16 cross 2 LCD, I am going to use it in a 4-bit mode. So thereby I am going to connect D4 to D7 to 3.4 to 3.7, and RS, register select line, is connected to 3.2, enable line is connected to 3.3. So RW bar, we are going to connect it to ground. As our microcontroller is going to keep on writing the data, we are going to connect this RW bar to ground. The other 4 lines D0 to D3 is connected to ground. Same way VSS is connected to ground. VEE, which is usually used for contrast adjustment also, we are going to connect it to ground, which means I am going to have a high contrast. Then VDD line, which is connected to your supply. Then from microcontroller, port 2.0, 2.1, 2.2, we are going to use it as a address lines for A, B and C, which will be given to your ADC 0808 IC. Port 2.3 is used as a ALE line, and port 2.6 is used as a start the conversion process. Port 2.7 is used as a end of conversion process. So this is a typical circuit which we are going to build in a Proteus 8 environment. Now let us look at the embedded C programming part. How to fetch the data from ADC and how to display it on a LCD. So here first initially we show that the LCD RS is connected to port 3.2, enable is connected to 3.3, D4 is connected to port 3.4, D5 is connected to 3.5, D6 is connected to 3.6 and D7 is connected to 3.7. So this gives the typical connection of your microcontroller with the LCD. Then we are going to declare few variables, and in the main program, since we have connected port 1 to the ADC, so we need to read the data from ADC. So port 1 needs to be configured as an input port. So for that we specify a value of 0xFF, which means all the port 1 pins are configured as an input port pins. Port 3 we are going to connect to your LCD, so we need to configure it as an output port. So port 3 equal to 0x00. So a value of 0 to the port pin will make the port pin to be in output. A value of 1 to the port pin will make the port pin to be in input. Then port 2.0th pin, we are going to use it for address A and it is configured as output. Same way 2.1 is for address B, it is also configured as output. 2.2 is used for address C, it is also configured as an output. 2.3 we are going to use it as an ALE, which is also configured as an output pin. Port 2.6 is used for start the conversion process. Again it needs to be given by our microcontroller, so it is also configured as an output pin. Port 2.7, which is used as a end of conversion line. So this end of conversion line will be coming from your ADC. So we need to read that end of conversion status. So it is configured as an input pin. So after configuring the ports as output and input, we need to set the address for your address A, address B and address C. Since we have connected LM35 to IN0, so we have set the address as 000. And in order for this address to be latched, ALE is set to 1. So thereby this address will be latched, IN0 will be selected. So after all the configuration process, we need to configure our LCD through LCD initialization. Then we are going to send a command so that the cursor gets put off. Then again another command to clear the buffer register in your LCD. Then we are going to declare two arrays, text and text1 with LM35 temperature and sensor interface. And we are going to put this value onto the LCD. So in order to put the value onto the LCD, we will be using a function called as LCD_out. 1,1 represents first row, first position. We are going to put this text, which is nothing but your LM35 temperature. In LCD_out, 2,1 represents second row, first position. We are going to put this text1, which is nothing but your sensor interface. So in order to retain this output for some time duration, we retain it using the delay function for 2 seconds. Then in a while loop, we are setting the variable to be 0, ADC_RD equal to 0. Then we are going to start the conversion process by providing port 2.F6 equal to 1. So the conversion will start by the ADC. So we wait for 1 second. After 1 second, we stop the conversion process by giving port 2.F6 equal to 0. So after 1 second, I am going to read whether my end of conversion is achieved. So end of conversion is checked using your port 2.F7. I am checking whether it is 1, which means the end of conversion has achieved. So once end of conversion is there, we read the value from port 1, send it to a variable called as ADC underscore RD. So this ADC underscore RD will have a binary bit pattern. We need to convert this binary bit pattern into a voltage. So for doing that, what we do, we take the binary bit pattern, multiply it with the resolution of your ADC. So as I said, resolution of your ADC is 19.61 for a reference voltage of 5 volt. So now we get the voltage value in the temporary variable. So I need to convert this voltage into a temperature. For converting voltage into a temperature, we take this temp divided by 10, because we know that for LM35, for every 1 degree centigrade, it will produce 10 millivolt variation. So I take the voltage value divided by 10, so thereby it gets converted into temperature, and that temperature value goes to your temp variable. So again, this temp variable is in a binary format. We need to convert it into a ASCII format so that it can be displayed in your LCD. So in order to do that, we use this int to string function. Integer data to string function we use. So we convert this temp value and convert it into a string in the variable called as temperature. Then we are going to clear the buffer register in the LCD. Then we are going to print in the first row, first position, temperature. In the second row, first position, we are going to put in C equal to. Then after that, we are going to display our temperature which we have measured. Then after some locations, we are going to put C to indicate it's a centigrade temperature. So we wait for 2 seconds. Again, since it is in a while loop, again we start the conversion process, stop it after 1 second, then check whether end of conversion is achieved, again do the same process. So for every 2 seconds, the data will be read from your ADC and it will be displayed onto your LCD. Now let us look at the circuit diagram in Proteus. So here you see the Proteus where we have built the circuit. So here a temperature sensor LM35 is connected to this ADC0808 IC, and the value from the ADC is read by your AT89C51 Microcontroller, and the value will get displayed in your LCD. So in micro C Pro for PIC, we have written the code for your program. So here, as I said, we have the connection diagram, how this LCD is connected to the port lines of your microcontroller. Then port configuration, set the address values, then we measure the ADC value and send it to your LCD. So once programming is done, we build the program